So hello everybody, my name is Kaan, and I'm a final year PhD student from ETH Zurich Systems Group. I will talk about some of the work that we have done in the past, trying to accelerate database workloads in database analytics and machine learning. And also, I have spent this summer at IBM Zurich labs working on OpenCAPI and HBM and trying to see how these can help us with our previous efforts and maybe enhance them. So I will try to give you an idea about those works. So the obligatory motivation slide, I think most of you are familiar with the trends ongoing. So on the one hand, we have data processing getting more complex. Data sizes are increasing with IoT and everything going on in that space. But also the workloads that we are performing on this data are getting more complex, right? So mainly driven by machine learning, deep learning. We want to perform more compute-intensive workloads on the data that we are gathering. On the other side of the spectrum, however, when we look at the hardware evolution, we see that technology scaling is slowing down. The frequencies don't scale anymore for a decade or more. But nowadays, also the Moore's law is slowing down, so we cannot put more transistors onto the chip area. So the question that we ask in our group is, how will future systems deal with these trends? And one major direction seems to be that hardware being specialized, right? So across the board, we see specialized hardware solutions. GPUs are widely used for deep learning tasks. These are throughput-oriented workloads, especially training. So you can batch a lot. You can gain advantage from dense linear algebra. So their GPUs help a lot. Then we see recently FPGA deployments in cloud providers, right? So for instance, Microsoft is using FPGAs a lot in their data centers. Amazon is offering F1 instances to the end users to use FPGAs. Many of you have used them before. Intel has been working on this platform where they combined FPGAs and CPUs with a coherently attached interconnect, very similar to OpenCAPI, but OpenCAPI's advantage is, of course, that it's open source, and many different vendors provide this, right? So we have this advantage. On the other side of the spectrum, there are also many ASIC solutions. So for instance, Tensor Processing Unit from Google is targeting, again, deep learning, mostly training, but they have also been looking at inference on the edge recently. For database processing, Oracle had this chip, Spark M7, which they canceled because they are moving more into conventional processors, which adopted these specialized instructions that they have been doing. And also even Tesla has a self-driving chip. So there's a lot happening in that area. So in terms of our research, we work a lot with FPGAs in our group because they have a couple of advantages. So first of all, they are very flexible in terms of the architecture. Right? So wide exploration capabilities are possible in terms of the computation, but also in terms of the system integration. So we can integrate the FPGA as a coprocessor next to the CPU, as a standalone processor, or even network attached. So we have done some work in our group, for instance, developing a TCP/IP stack to be able to allow FPGAs as a standalone thing, as a standalone processor directly attached to the network. And also, as I mentioned, they are increasingly available in clouds, so people are looking into ways of how we can utilize them. So let me tell you a little bit about the scope of my research specifically. So I am interested in systems where the FPGA is attached as a coprocessor next to a CPU. And on the CPU, we have an in-memory database in which we want to run OLAP, so this is online analytical processing workloads, and machine learning. So in this system, we have asked a bunch of questions. So the first question that I have dealt with is, okay, if you want to accelerate something, which workloads actually benefit from acceleration in this type of system, in an in-memory database? So we have done some work on robust hash functions, high fan-out data partitioning, quantized stochastic gradient descent for linear model training. So we found out these workloads benefit a lot from FPGA acceleration. The second question is about integration. So can specialized hardware or FPGAs help when we integrate novel workloads to the database? And there we found out about performing, again, training on column store databases. We have extended the quantized SGD work to work on a bit weaving format to do, again, quantized linear model training. And finally, our efforts have converged into a system we call doppioDB. So this is more about the third question that we're asking. How can we actually increase the utilization and sharing of these accelerator efforts, right? And there we have a solution called doppioDB, which I will explain in a couple of slides, where we try to integrate our previous efforts into a final end-to-end database solution. So in this talk, in the rest of the talk, I will mainly focus on these three things. So I will talk a little bit about the data partitioning work, how this helps accelerate the join operation on a CPU plus FPGA system. I will talk a little bit about performing machine learning in a column store database, and I will also talk about doppioDB. So as I mentioned in the first half, the focus will be on our previous work. So I will talk about an overview about doppioDB and consider the system first from a relational processing perspective, where this will be focused on the partitioned hash join, and then also look at from the machine learning perspective to this system, and introduce the training models on columnar storage. In the second half of the talk, I will talk about the opportunities with OpenCAPI plus high bandwidth memory. Right? So how does the system architecture look like if we consider these two things? What are the pros and cons? I will show you some micro benchmarks that we have done when we developed an infrastructure around these aspects. And finally, I will talk about the ongoing efforts about using our previous efforts in this domain. So let's start with doppioDB. So we call this hardware accelerated database. So what doppioDB is actually a combination of multiple things. So one is we took an main memory open source database, which is MonetDB, and this platform, the doppioDB was initially implemented on the first generation of Intel Xeon Plus FPGA, but now we have extended it to use also the second generation, and now we have efforts to make it portable across multiple platforms and hopefully OpenCAPI also. So we take a CPU plus FPGA system where the FPGA has coherent access to the main memory of the CPU, and we have a framework called Centaur that actually helps combining these two platforms. Right? So what Centaur does is it has a memory manager to be able to do malloc and free on the memory that the FPGA can use, and also it has a POSIX threads-like interface, which we call F threads, so FPGA threads. So the operators that we implement on the FPGA side can be used in a transparent way, as they look like software threads when you use them, right? So what happens is, what Centaur does is, per job type, so there might be multiple jobs on the FPGA, and per job type or operator type, there are queues, and the queues are going to be served in a first come, first served basis, which is a pretty naive scheduling method, but it works for this type of throughput-oriented systems, right? So this is what allows us to implement different type of operators and then use them within the database by using the abstractions that are allowed by Centaur. Right? So this is basically what doppioDB consists of. So how can we use the hardware operators? How does it look like from the database perspective? We can basically, once we integrate these operators into doppioDB, we can use them directly from SQL. Right? So this is our idea. What happens is the tables or the columns in case of MonetDB are stored in the main memory, and then the FPGA can access the main copy of the data. So this is a really no-copy system, which is allowed by the coherent interconnect. Right? And I'm showing you here two examples. One is the partitioning work that I will be talking about next, and then the next one is training. So let's say you want to use these two different operators that are on the FPGA. You can either use a user-defined function from the SQL level, for instance, to initiate training here, or if it's a more integrated operator, such as the partitioning, which is used as part of a join, then this is going to be happening transparently. So the user will not see the usage of the FPGA. It will just be like a normal SQL query where a join will happen, and the FPGA will be used automatically by the query engine. So these are the two ways of using the operators. Just showing doppioDB in action here, we have an example that is actually from the demo that we have shown in VLDB this year, so this was in August. So what we showed here was, in a system, imagine you want to perform some training jobs, plus some traditional query processing, right? So you have you have 5 queries here that scan the data, perform selection, perform joins, plus you have 1 training job that you want to run together in the same system. So if you just use the CPU, you can see, first of all, the training throughput is around 5 gigabytes per second. So this is the rate at which you can consume the data. Secondly, if you look at the response time for the traditional queries, it's going to be very non-deterministic, right? So there are going to be jumps. Why? Because the CPU utilization is pretty high, so it's around 50%. Whereas with the capabilities of doppioDB, we can run the training on the FPGA, reaching around 6 gigabytes per second. The query response time for the rest of the database, it will be more deterministic because the CPU utilization is much lower, around 20%. So this is just one of the use cases where doppioDB is pretty useful. So with that, let me actually jump into the first use case and introduce you to this use case in more detail. So this is about the relational processing perspective, and we are considering the partitioned hash join algorithm. So what is relational query processing? So for the uninitiated, I have a very brief introduction. So relational query processing is about performing operations, performing queries and analysis on relational databases. And in relational databases, we have so-called tables, right? So for instance, we have students here, student name, age, and then a table called takes lecture. So these are students referenced by their names. That's why they are called relational, and the lecture name that the students take. So let's say we want to find out the sorted average age of students taking a certain lecture. So how does this look like in SQL? When we write the query, it looks something like this. So we perform a selection, and then from both tables, students join takes lecture on student name, and a selection on the lecture name. A group by is an aggregation, and finally a sort. So the details are not very important, but the important thing is this can be quite data and compute intensive, right? So performing this query. So first of all, this has to perform string matching, then join 2 tables, aggregate, which is the group by operation, and finally sort. So there are a lot of things going on in the background, right? So if you focus on this query, one of the most expensive parts is joining 2 tables. So that's why for the first effort, we focused on this. So how can we accelerate this, or how can we improve this by taking advantage of the new platforms, right, where the FPGA has access to the main copy of the data, and a hybrid processing between the CPU and FPGA is enabled. So before I dive into that hardware-specific details, let me give you an overview about the join algorithms. So there are many join algorithms with respective pros and cons. So depending on, for instance, the join cardinality on both sides, you might choose different algorithms. But it has been shown that the partitioned version of joins are very efficient on multi-core CPU platforms, right? So, for instance, a hash join, a normal hash join, how it looks like in MonetDB is something like this. So you have two columns, and you want to find the matching numbers and give the matching indexes, right? So what MonetDB does is it first builds a hash table on the smaller column, and then it probes the large column and scans the hash table for any matches. And whenever there's a match, it will actually push out a result with the indexes of the matching numbers, right? So this is a very simple hash join implementation. Now the problem with this implementation on a multi-core CPU is if your hash table does not fit the cache, you have a problem, right? You are going to be latency bound when you probe the hash table from the DRAM of the CPU. So that's why people have figured out another algorithm that first partitions both sides of the join, and these partitions, the partitioning is done in a high fan-out way, such that each partition will for sure fit the cache. Ideally L1 cache, but in some cases, if the data sets are too large, it's going to fit the L2 cache. So if this is the case, the join will run much faster, right? Because you don't have the problem here anymore, where you have to be bound by the latency of the DRAM. However, the expensive part about this algorithm, the partition task join, is the partitioning phase. So we thought, okay, can we actually accelerate the partitioning phase on the FPGA and let the CPU do the rest of the work, right? Let the CPU do build and probe, which it's very good at. So it's very hard to beat the CPU on this part of the join, because everything fits the cache. It's going to be very efficient. It's clocked much faster than the FPGA, right? So we are focused on the partitioning phase. So in the coprocessor deployment, what we did is we implemented a so-called partitioning engine on the FPGA. The data, the tables reside in the DRAM of the CPU, but the FPGA has coherent access to that DRAM. Keep in mind, the FPGA's bandwidth is much lower than the CPU. So it's on this platform. This was the first generation of the Xeon Plus FPGA. We got around 6.5 gigabytes per second. So what we do is we pass the pointers of these columns to the FPGA, to the partitioning engine. It does the partitioning, writes the results back, and at the same time, it also builds those histograms. So these histograms show which of these partitions contain how many tuples, right? And once we have these histograms and the partitioned results, we can just allocate these to the CPU cores, and then they will do the rest of the job. So it's going to be very efficient. Now the question is why the partitioning is good on an FPGA compared to a CPU, right? So there are a couple of things to consider here. So this is the actual architecture of the engine, which I'm not going to talk about in detail. But the advantages on the FPGAs, first, you can do hashing very robustly. So you can use the best hash function that you can come up with, and then the FPGA will handle it because of its vectorization and pipelining capabilities. Secondly, you can do very efficient write combining. And write combining turns out to be very important for doing good partitioning, because it's a very random access heavy workload when you write the partitions to the memory, right? So what happens is you have to combine multiple tuples that belong to the same partition in a cache line or even larger buffers, and then push them to the memory to be very efficient. And finally, of course, we can take advantage of pipeline and SIMD parallelism on the FPGA. So for instance, here we do hashing and write combining all in a pipeline manner, right? So we achieve very high throughput. So let's take a look at the throughput numbers. So the red bars, on the x-axis, I'm showing you different configurations, and on the y-axis, I'm showing you the throughput in million tuples per second. So the red bars are from related work. So for instance, the first bar is from a CPU optimized work, which uses a 32 core machine. The second one is from an FPGA work. So the blue ones are our implementations on the Xeon Plus FPGA platform. So we can see that with the best configuration where we perform padding and virtual row IDs, so this is like implementation specific details, we can beat the related work by around 2x, but we are still much slower than a 32-core CPU. Although we match the throughput of our CPU, which only has 10 cores. So this is already a good outcome, but if you think about the bandwidth limitations of this workload, this becomes even a better result, right? Because here we are bound by the 6.5 gigabytes per second memory bandwidth. If we don't consider the bandwidth limitations, we can actually see this is what we achieve in terms of the internal throughput on the FPGA. We can achieve much higher partitioning throughput even compared to the 32-core CPU. So this was a good outcome, and one of the advantages of this work was we can combine this partitioning engine now with the rest of the joint, so we can achieve an end-to-end solution, right? And this is what I'm showing you here. So this is an end-to-end join operation performed using the FPGA partitioning. On the x-axis, we have the number of threads that we use on the CPU when we do the build and probe and partitioning, if we do the partitioning on the CPU. And on the y-axis, we have the time. So what is interesting about this graph, in my opinion, is, first of all, the partitioning time is going to be very different on the CPU depending on the quality of hash function that you use. So if you use a higher quality hash function, you get around 20% slowdown on the CPU because it cannot handle it, right? If you use just one thread. And to match the performance of the FPGA, you have to use 8 cores. If you use 8 cores or more, the CPU is actually going to be faster than the FPGA because it has many more resources, right? It has more bandwidth to the memory and so on. So this was a positive outcome in that in the time that we have done this, and we thought, okay, what if we had more bandwidth? What if the FPGA had more bandwidth? Right? So this is something that the high bandwidth memory might benefit, as I will talk later on. But for now, let's move on to the other perspective, the machine learning perspective, which I think is actually more interesting in terms of FPGA-based acceleration. So here we are talking about training models on columnar storage. So what we want to achieve in this work is generalized linear model training in a column store database. What are generalized linear models? So these are very widely used models. These are not deep learning models, but this is still the more widely used machine learning models in the industry and in practice. So for instance, logistic regression, support vector machines, it's not as popular nowadays as deep learning because deep learning can solve more complex problems in vision and natural language processing, but these are still the workhorse algorithms in terms of usage. And they are utilized in many cases in the database. So these are relevant models for the types of data that reside in the database, relational data. Right? So we asked the question, how can we integrate this in a column store database without disrupting either database efficiency or ML quality and performance? And here what I mean by database efficiency and ML quality and performance are these things. So by database efficiency, I mean columnar storage, which is very important to achieve high performance on analytical workloads, and compression capabilities, which I will introduce in the next slide. On the ML side, what we mean by quality and performance is maintaining high throughput training and also fast convergence. So we want our training algorithm to be high quality. We don't want to use many iterations until we converge to the solution. So this is our goal. And the first challenge when we try to do this is the data layout. So if you think about it, database management systems are highly optimized systems. They are highly optimized for the CPU. And when you try to integrate new algorithms, you're going to face a couple of challenges, right? So the first challenge is the data layout. What happens here is I have a table which is called students. So you can store this table either in a row store or a column store. So in the row store, you store all the rows together sequentially in the memory, whereas in the column store, you store all the columns together. in the memory sequentially. So the column store is better suited for selective data access, complex analytics when you perform a lot of joins, and also they can be easily compressed. Why? Because you store the same types of data points next to each other. Okay. So this works very well, and it's used. The column store is the standard format that is used in analytically oriented database management systems. So they have a lot of advantages. But if you look at the machine learning algorithms, the most popular machine learning algorithms that perform training, such as SGD, they access data in a row-wise fashion. So this is obviously a mismatch, right? So what happens when we run SGD on a column store? So on the left side, we show the SGD for linear regression, which is quite straightforward. So when we perform this algorithm on a row store, it accesses data in a perfectly sequential way. Right. So you get very high memory bandwidth because you are not jumping, you are not doing any strided access. However, if you perform this on a column store, you almost get random access, right? And the memory bandwidth suffers a lot from that. So if you perform this experiment on a CPU, we see that the processing rate from SGD row to SGD column drops around 23x. So this is a huge performance loss if you want to perform this. So the next question that we asked is there an algorithm working natively on column stores? And it turns out there is actually. There is a family of algorithms called coordinate descent methods that access data in a column-wise fashion. So when we use these stochastic coordinate descent algorithm, we can see that the tables are going to be accessed column-wise. And it's going to turn out to be very good in terms of the memory bandwidth utilization and final processing rate. But there is one problem with this algorithm, which is the intermediate state that it keeps, the inner product vector, can be quite large. And if that vector does not fit the cache, then the processing rate again drops. Right? So the intermediate state vector can be very large. And the way to solve that problem, especially if we consider implementing this algorithm on an FPGA, becomes very important. Why? Because the FPGA's on-chip memory is much smaller than the CPU's cache. Sure, there are ultra-RAM solutions becoming more popular, but still solving the cache efficiency problem or the scratchpad memory usage efficiency problem is very important, both for the CPU and the FPGA. So the way we solve this problem is we actually modify this algorithm a little bit to again use the partitioning trick. So instead of consuming the columns entirely, we consume them in partitions. And then once in a while, what we have to do is an averaging, model averaging, to broadcast the changes that happen in individual partitions to the entire vector. And it turns out this modification to the algorithm does not degrade the quality, but it increases performance a lot. So this solves our column store challenge. The second challenge that we are facing is the need for on-the-fly data transformation. So where does this need come from? As I mentioned, column store databases use compression heavily. In most of the cases, it's actually multiple compression schemes applied after the other. For instance, in SAP HANA, this is the case. And also in cloud databases, data is mostly encrypted. Right? So if you want to perform machine learning on compressed or encrypted data, you first have to decompress it and decrypt it. And this is going to be a huge performance killer. So here, what I'm showing you is performing this partitioned SCD algorithm on raw data, on compressed data, on encrypted data, and here on both encrypted and compressed data. And as you can see, if you look at the timing breakdown, if we have to transform data in any way, then the time is dominated by this transformation operation, right? Either decryption or decompression on the CPU. So the outcome is decompression and decryption time dominates on the CPU, and this is actually where the FPGA or specialized hardware comes into play. Now our hope is we can design specialized hardware to perform all these operations in a pipeline. Again, for this work, we use the Intel Xeon Plus FPGA, and what we have done is we have designed a specialized pipeline. So this is the compute engine to perform the coordinate descent operation. And then we have 2 data transformation slots to do the on-the-fly data transformation. Right? So what this does is, first of all, it has a very efficient memory access engine. We call this the fetch engine. So it prefetches the addresses and then accesses data in a bulk, which achieves the memory bandwidth. And then we have the data transformation in pipeline with the ML, and we have a highly parallel computation engine for doing the coordinate descent. So if you look at the throughput results, on the x-axis, on the left, I'm showing you the CPU with highly optimized code using all the AVX instructions and 14 cores on this platform. And on the right, we have the FPGA. We can see if you have the raw data, the CPU is very fast, right? So it actually reaches the memory bandwidth of the CPU around 50 gigabytes per second, thanks to all these optimizations. But if you use either compressed, encrypted, or transform data in any way, the performance drops a lot, whereas the FPGA is able to maintain a high performance across the board. And again, the FPGA is limited by the memory bandwidth. On this platform, it's around 18 gigabytes per second. So this was the outcome of that work. We were able to convince the database community that this is interesting work, but again, we are limited by the platform, by the memory bandwidth, right? So now we come to the question: how does OpenCAPI+HBM help in that sense? So as I mentioned, in these systems, where is the usual bottleneck? The bottleneck is usually in this arrow here. When we access the memory of the CPU, we get around, let's say, in the best case, 20 gigabytes per second. Right? So the memory access of bandwidth of the FPGA is usually much lower than the CPU. Even if you use OpenCAPI, this is still the case, right? So the CPU is going to be much better at accessing its own data rather than the FPGA. So now with these new platforms, with high bandwidth memory, what we have instead is an HBM, which is in the order of 8 gigabytes or 16 gigabytes, depending on what board you use. You get around 400 gigabytes per second potentially, right? So this is going to be a huge advantage for many workloads. And what we want to explore is what workloads really benefit from this. What are the pitfalls? So in the first glance, it looks very nice, but what are some of the challenges related to that? So during my internship at IBM Zurich Labs, I tried to solve these problems. So I tried to first develop an infrastructure that would enable the usage of this platform, right? So what we have on the target board, this is an Alpha Data 987, we have 2 HBM stacks, and this gives 16 Axis-3 slaves each, and potentially we can reach 400 gigabytes per second. Now the question that we're asking is how to connect these parallel engines. So we will have some type of scale-out parallels, right? So we will have multiple engines, but how to connect these engines to these stacks, how to really utilize them, how to balance the OpenCAPI bandwidth that we have with the HBM bandwidth on this platform. So the first challenge is there is no framework for this platform currently like Snap. Snap is very good for CAPI2, and recently we have seen it's been released for OpenCAPI, but Snap does not support these multiple engine things. And from a database perspective, it's very important to be able to use multiple computation engines and to be able to use them in an asynchronous way, right? So this is one of the challenges that we are facing when we design infrastructures. Another consideration for highest bandwidth utilization, you have to actually access these 2 stacks in parallel. So you have to somehow design a shim between the engines and the stacks so that the accesses are routed to both of them at the same time. How do we connect the engines to the HBM and OpenCAPI? Do we allow all of them to access both sides? But that would create a bandwidth imbalance. So how do we take care of that? And do we use, for instance, 32 engines because we have 32 Axis-3 slaves? But for most things, using 32 engines will be challenging for timing, for resource consumption, and so on. So these are all the challenges that we'll be facing. So what I came up with, or what we came up with together in the group is an infrastructure like this. So what this does is, it first has a control request and receive blocks that are kind of the interface to the OpenCAPI side to talk to the CPU, to receive data from the CPU's memory. These are all very standard operations. But then on the FPGA side, what we have is we have two data movers. So the data movers are responsible for moving the data between CPU's memory and the HBM. So these are the only two blocks that are able to access both sides. And then we have, in this case, just 7 engines accessing the HBMs via this static HBM stack shim, which routes the request always in parallel to both stacks to maximize the bandwidth usage, right? So in this type of architecture, our goal is to maximize the bandwidth, balance the data access requirements from both OpenCAPI and the HBM, and also allow a practical deployment of whatever acceleration efforts that we might come up with. Right? So on this system, what we have done is we have first measured the bandwidth. Okay, how much can we get? Can we really reach 400 gigabytes per second when we access HBM? So this is what we achieve. So on the x-axis, we have the number of engines from between 1 and 7. And on the y-axis, I'm showing you the total bandwidth in gigabytes per second. As we can see, if we just use the same address space, so if all the engines try to access the same address space, the bandwidth actually doesn't scale at all, right? It actually remains constant. And this is bad news. If you don't prepare your data in the HBM in a way that the engines will access separate address spaces, you won't see any bandwidth advantages. And secondly, the good news is if you actually prepare your data in a way that the address space is spread, then you can gain almost linear increase in the bandwidth with the number of engines that you use. So at most, around here we get around 230 gigabytes per second. Why don't we reach 400 gigabytes per second? So there are a couple of challenges related to more engineering work. So axi clock is 300 megahertz instead of 400 megahertz because of timing issues we faced. So the device is an engineering sample device, and we use 14 interfaces rather than 16 because 2 are reserved for the data movers. So this is what we measured on the infrastructure that we have. Now looking back, can HBM help partition hash rate, let's say? So we had this use case where we did the partitioning on the FPGA and the build and prop happened on the CPU. So unfortunately, the HBM, in my opinion, does not help with this workload because this workload is really based on hybrid processing, right? So the data needs to be accessed to and from CPU's memory. And if you do that, the bandwidth limitation will be on the OpenCAPI side and not on the HBM side. So we really, when we wanted to accelerate join algorithms with this deployment, we had to come up with a different join algorithm. What happens in this different join algorithm is we don't do any partitioning. We just replicate the smaller side of the join across multiple engines and then consume the larger side in parallel to create a scan-heavy workload. Right? So this workload is going to be scan-heavy, but the advantage over a high-end CPU is still not clear, especially if the CPU has high memory bandwidth. So this join engine that we have implemented looks something like that. So as I mentioned, we have hash tables that are replicated. So in the first phase, the smaller side is read from OpenCAPI. Actually, in this version, it was Snap plus copy 2. We build the hash tables, and then the large side of the join is read and stored in the DRAM, and it will be HBM in the integrated case. And we will finally probe the larger side and push out whatever join result that we have. So this work we have implemented with Snap plus copy 2, and we didn't have HBM ready by that time when I worked on this. But now our efforts are focused on taking this, whatever we have here, because we got good results. I mean, we can achieve 15 gigabytes per second. So if we can deploy this in an HBM platform, hopefully we can gain the same bandwidth advantages as we saw before. So can HBM help machine learning? I think here we have an easier story to sell, right? Because during training, a data set is accessed iteratively and regularly. So it's fine if you just copy the data to the HBM. And most algorithms can also be parallelized in a scale-out fashion. So you can easily saturate the bandwidth and take advantage of it. Is HBM size a limitation? What if your data set does not fit, let's say, 8 gigabytes or 16 gigabytes? It's not a problem. Even if the training data set is larger than 8 gigabytes, training can run on partitions, as I mentioned, right? So you can partition the thing, the data set, and then run a couple of epochs on one partition and then move on to the next one. So that's fine. And also, ML operations tend to be on warm or cold data rather than hot data. So this is data that is not usually touched a lot. So you want to consume it a lot, but it's not going to be updated. So it's fine if you have a separate copy of that data in the HBM and then just reuse it. That's why I think ML is going to be much easier to accelerate with HBM, and this is also one of the efforts that we are spending time on currently. All right, so let me conclude. So as I mentioned, I mean, specialized hardware has many potentials for improving in-database advanced analytics. In our group, we mainly focused on two perspectives: relational processing and machine learning. So with relational processing, utilizing FPGAs is really, really difficult. So you need to think really carefully about your problem. First of all, software systems are highly optimized, and it's hard to compete with a high-end CPU, especially if the data needs to be moved. This is the case even if you think about general purpose GPU processing. If you need to copy the data all the time and then you touch the bytes just once or a couple of times, it is probably not worth it to do the acceleration, right? And this is why it's useful only in limited use cases. Whereas on the machine learning side, I think it's a better story because the algorithms are more compute intensive, and when you want to integrate these novel workloads into the database, they do not fit well with existing systems, and utilizing specialized hardware there helps a lot. So in terms of the OpenCAPI and high bandwidth memory, what we think is, so again, utilizing HBM is going to be difficult for relational processing, for, let's say, join operations. For other operators that are very frequently used and that actually reduce the data, for instance, an aggregation or a selection, like complex selection algorithms such as regular expression matching, as was talked before, there we really might have an advantage. Right? And for machine learning perspective, I think it's going to be also very, very useful. So that's it for my talk, and I will be happy to take any questions and also discuss offline about any questions that you might have.